Başak, right? Başak has a question. She says that why did you plot this electric field in that direction? Because I was wrong. It is in this direction indeed, but we are pulling in against it. Okay, you are right. So please make sure that at home you go over this problem again and figure it out yourself as well. Okay. Now we are going to solve another problem. We are actually going to solve the same problem, but we will be solving it with battery. And it will turn into a Sherlock Holmes mystery. Yes. We are going to find some problem and we are going to try to find who is responsible, what is responsible for that problem. Let's do it not that slowly. I think when I go slowly, you are more confused. Yes. I think if I go quickly, we will make more progress and more efficient progress, actually. Plus, we are quite familiar now with the problem. So let's go X. This is the area A, potential V. All right. Situation 1, UA at the beginning, UB at the end. So let's find UA. Can you tell me what is UA? One half CV squared. Do you agree? What is that? 1/2 epsilon 0 A over X V squared. Do you agree? Very good. What is UB? 1/2 C prime V squared, which is 1/2 epsilon 0 A over 3X V squared. And that's it. Do you agree? Good. Now let's find, this is UA and UB. And what is UB minus UA? It's UB minus UA is epsilon 0 A V squared over X times 1 over 6 minus 1 over 2, which is 1 over 3, but with a negative sign. So UB minus UA is epsilon 0 A V squared over 3X with a negative sign. So far, so good. Did you follow this? Now let's do it with force, from force. You remember, for any distance y, we had Fy, and this time Fy will depend on y because of the battery, right? Q will not be the same always. So Fy will be Q times E y, and Ey will be what? Sigma over 2 epsilon 0, so Q times Q times Q over 2 epsilon 0 A, so Q squared over 2 epsilon 0 A, but Q is not constant, so it depends on V. So let me just write it down like this: C squared times V squared over 2 epsilon 0 A I feel like I'm showing my ear by doing this, but I will not stop. I will just go all the way, and if you find any mistake, just let me know. Are you following? Of course, just one moment. While I will listen to your question, please, the rest, just examine all the mathematics here. What's the question?
Since E is not constant, shouldn't we take the differentiation of V? Because in that case, still don't we think like doing this formula to think like E is constant?
Okay, so E is not constant. E at a distance y is simply V over y. Do you agree with this? Yes? So let me just plug this formula over here. Then f of y is simply q times v over y, right? But q is not constant as well. Q is cv over 2. Q is cv, right? Q is cv, which means that this is epsilon 0 a over y times v over y. Do you see we arrive at the same result, except for v over y is, okay. EY is not v over y, it's v over 2y, because we are not taking the electric field just by itself, we are taking half of the electric field, remember? Okay. All right. All this you can figure out, but I'm sure that this is the case. Now let's take the integral. Let me take the integral. W is integral fy dy from x to 3x, right? E0 a v squared over 2 integral dy over y squared x to 3x. What's the integral? Do you agree with this? Any problems, just let me know whenever you have a problem. We need to be careful, very, very careful. Seems like we are going on the right track. Right? So what do we get? Minus, no, not minus, just epsilon 0 a v squared over 3x. Do you agree? Yes? Let me just take it over here. Do you see the problem? Do you see the problem? Everyone? No, you don't see the problem? You don't see the reason. Yeah. But you do see the problem, and the problem is that work done seems to be negative of potential energy change. Although we do know that it's the work done on the system by us, right? So where is the mystery here? Why did we get negative sign? Do you understand the question? You don't understand the question. Yes. Let me rephrase. So in the previous version, when we didn't have the battery, right, UB minus UA, as expected, turned out to be W. But now, we don't have UB minus UA equal to W. Why is that?
We couldn't do the work. The battery did the work.
We didn't do the work, the battery did the work. Brilliant. You know, like how Sherlock Holmes, the gardener, is always there doing its thing, and it turns out he is the killer. Yes, the battery is the gardener here. Okay, so what's going on? We are doing work on the system, but then we are writing the change in the energy of only part of the system, which is the capacitor. We should also consider the change in the energy of the battery. Do you see it? Yes? Although we are interacting only with the capacitor, but when we change the distance of the capacitor, the charge, does it increase or decrease? It decreases. It decreases, and the charge goes to the battery, charging the battery. So that's where our positive work goes. All right? Good. Let's then figure out. So this is UB of the capacitor. All right? UB minus UA of the battery can be found. So we know that the potential difference of the battery is always the same, V. This difference in energy is going to be V times delta Q. The amount of charge that goes to the battery. Do you agree with this formula? Yes? Because there is a potential difference, and we are adding charge on top of that potential difference. So what is delta Q? Delta Q is QB. It's not QB minus QA, it's minus QB minus QA, because what's going on here is you had some Q here, then you have less Q here. So more Q minus less Q is equal to the charge that went to the battery. Meaning that it's not QB minus QA, it's QA minus QB. Are you totally and irreversibly confused?
Yes.
Okay. Good. So go home and get unconfused, please. QA minus QB. Can you tell me QA minus Q? What is QA minus QB? Delta Q, yes. Which is? C2 times C1 times V. CA times, let's call it CA times V minus CB times V, right? Which is equal to epsilon 0 A over X times V minus epsilon 0 A over 3X times V, which is epsilon 0 A times V over 3X with the 2 in front of it, right? So U battery B minus U battery A is 2 times V over 3X times V. So it becomes this one, and this is due to the capacitor. Copy and paste it here. This is due to the capacitor, this is due to the battery. U total B minus U total A is indeed epsilon 0 a v squared over 3x, which is indeed equal to the work done. Yes.
Doesn't our potential energy formula have a Q in the denominator? Like where did the Q go?
Very good question. You mean here? You mean over here, right? Over here, very, very good question. This is for the battery, it's not for the capacitor, right? So you charge the battery and the capacitor differently. When you are charging the capacitor, the amount of charge you put at a certain time actually changes the potential, right? So you get a q dq integral, which gives you q squared over 2. However, when it's battery with the same potential and you are putting charge in it, it's just q times v. Did you get this? Kinda. So let me just write it down again. So for the battery charging, in the battery charging case, this v is constant, and you put q here, right? Plus q. So this is minus q, and to take dq from here and put it there, you need a work of dq times v, which is constant, right? And w in total is big Q times v. This is battery charging. Capacitor charging, then you have v is variable, right? V is variable. It's equal to what is it equal to? Q over C at a certain point, right? This is Q minus Q dQ. So dW is dQ times potential, which is Q over C. W is Q squared over 2C, which is 1/2 QV. Do you see it? Do you have a question? Are you worried? No. Good. We can start a new subject, which is dielectrics, and this is the last part before the exam. So we usually use dielectrics between the capacitors to increase the capacitance. Basically, you might have two plates. Let me just, instead of plotting it like this, imagine your typical parallel plate capacitor, and it has some capacitance, right? Now, if you fill in between, we assume so far we assumed we have vacuum. Okay, when you have vacuum, you have capacitance equals epsilon 0 A over D. All right. Now let's duplicate this and put something in between. So I'm going to put a material. How should I draw a material here? Some sort of a material in between. And this material is non-conducting, okay? And that non-conducting material in between is going to serve us as a dielectric. So any non-conducting material can be thought of as a dielectric. And we will see that dielectrics increase the capacitance. Capacitance becomes something called K times epsilon 0 times A over D. What is K? K is the dielectric constant. You are a bit tired, so I don't want to go into too much detail of physics of this. So for now, I will come back to the physics. But for now, it's just K, just like in high school. You have seen dielectrics in high school, right? It's just something that increases capacitance. For now, just that one. Then we will come back to its microscopic reason. For now, this is the case, and let me give you a couple of knowledge about K. So K is 1 for vacuum. Okay. And correspondingly, we are talking about epsilon 0, which is permittivity of free space. Okay. Whenever K is for a dielectric, K is different than 1 for a dielectric. And that corresponds to epsilon, which is epsilon 0 times K, which is permittivity of that material. Just permittivity. So I give you a material, you will tell me that the permittivity of this material is this. It's always larger than, okay, let me not generalize it. In a dielectric, it's larger than that of the free space. But otherwise, it can go to crazy places, can go to negative. But that's a different story. Are you with me? Yes? So let me give you a couple of examples. Let me give you this example. I have a parallel plate. I put a dielectric here, but it's not all the way through. It's going d over 2 here. This is the whole system. This is d, and this is A. The area is A. What is the capacitance? Do you understand the question? Yes? We are going to sum them. Why? Maybe, you don't know. So what we do in these situations is we treat it as capacitors in series. Okay, so we think of this part with the dielectric as one capacitor connected to another capacitor over there. Okay, so we treat it like this. One capacitor over here, another capacitor over here. One has a dielectric within, and the distance is d over 2. The other one doesn't have a dielectric within, d over 2, but the areas are the same. So what is C1 and what is C2 and what is C? What is C1? As you can see, with the dielectric, the capacitance increases, right? So it becomes epsilon 0, it becomes k times epsilon 0 times a over d over 2. Did you follow this? C2 becomes epsilon 0 times a over d over 2. Okay? D over 2. So what do you get? K times epsilon 0 times 2a over d and epsilon 0 times 2a over d. And what is the total capacitance?
Yeah,
Yes. You should multiply them, divide by their sum. Do you agree? So equivalent capacitance will be C1 plus, C1 times C2 over C1 plus C2. It doesn't work with free capacitors, obviously. It's not C1 times C2 times C3 over C1 plus C2 C3. It's not, okay? How do you find it when you have three capacitors? 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. All right. C1 times C2, which is epsilon 0 times 2a over d times k times epsilon 0 times 2a over d divided by basically k plus 1 times epsilon 0 times 2a over d. So this takes out that. What do you get? C equivalent is 2 epsilon 0 a k over d times k plus 1. Okay? This is a typical example. Any questions? Yes.
So you basically, if there is some material between the parallel plates, you think like actually there is two different conductors, C1 and C2, then you calculate it.
Exactly.
So in this situation, you think like there is a series connection between these.
Yes. Exactly. Very good. Very good.
How do you?
This is how you do it. This is how you do it. And another natural extension of this could be this. Like you have a capacitor over here, another one over here, another one over here.
Right side is parallel.
Right side is going to be parallel. Yes, exactly. That's how we treat these systems. So we are going to have basically a system with K1 over here, and then there's a cable going to two capacitors like so. Okay, this one is K3, sorry. K3 over here, K1 over here. But you need to make sure that you respect all the areas and whatnot. Okay? So for example, this one is going to have area of A and the distance of D over 2. This one is going to have, let's say it's exactly at the half part, so it's A over 2, D over 2 here, D over 2, A over 2 here. Did you get it?
Mm-hmm.
Everybody understands this? Good. What do we do if there's a metal in between? What is K of a metal?
3.
Huh?
Less than 1 maybe.
Less than 1 maybe, maybe infinity, right? So we assume that K goes to infinity as you become metallic. So I know it's tricky to think about it, but let's say you have a parallel plate and you put a metal in between. So let me. That's like a cable. Brilliant. Exactly. If this is a metal, that acts like a cable. All right? So let's say this is d over 3. Let's say this is d over 3. Okay? Then you practically have a system which has this. And okay, I broke my color language, so let me just recover it. So this becomes a cable. All right? Sure.
But it's not infinite because it still has resistance. Maybe. It's not perfect.
K going to infinity is a bit hard to imagine. Okay?
But in that case, charges wouldn't across the other plane. I mean,
So that's the thing. I didn't explain you the atomic origins of this. So normally, dielectric is an insulator, so charges don't move. And they just polarize. They get polarized and they produce induced electric field. But when you have a metal makes sure that inside the electric field is 0. So when the electric field is 0, across the metal, the potential is 0. Potential difference is 0. That's why it acts like a wire. Don't bother yourself by K going to infinity. What does that mean? Just simply think of metals being wires.
But when, first example, the other two case,
This one.
empty space between them.
Yes.
I see. No. In the yes.
This one.
Yes.
It's just I couldn't draw it properly. Do you mean this empty space? Yeah, it's a matter of drawing.
Are those meant to be touching with each other, or
They are meant to be touching. Yes.
because the
Can they touch? Yes, they can touch. If it's an insulator, there's no problem. Does it make sense?
Actually, I was thinking about metal is conducting.
This is not a metal though.
Yes,
Yes.
but we are thinking about wires also, these antennas in the illustration.
No, we don't. When you have an emptiness in this illustration, for example, okay, we think of it as a separate capacitor. Do you see it?
Yes.
Yes. So if this was drawn properly, let's say it was not drawn properly, then you actually have yet another capacitor in between with air capacitance, and then yet another one over here that's parallel to other two, which also has permittivity of just epsilon 0 and K equals to 1. Okay. All right. What else can we do with capacitors? Let's. Sure. Yeah, yes, of course. I will translate.
Şimdi diyelim ki orada K3, K1 ve K2 belirttiniz ya. Diyelim ki K3 olsun, K1 ve K2 kadar boşluk olsun ama vakum olsun. Yani burası boş olsun. Yine iki tane kapasitör var gibi davranmalı yoksa çünkü oradaki o vakumun boşluğu şeyi etkilemez mi bu sistemi?
Yes. So your question is, you want to put vacuum in between this,
Direkt K1 ve K2'nin
or in between here? Where do you want to put your?
sadece K3 var, sonra K3 kadar bir boşluk var, sonra tekrar
Yes. So you want to have something like this. Yes. Then you have an extra capacitor over here. You have an extra capacitor over here.
Like K for epsilon T.
K is equal to 1 for that capacitor. All right? Okay. Let me think. Just give me a moment to think. Do this one more example, and it's not an easy one, and then we can finish. So to do this not so easy question, I first need to tell you what happens to the electric field when you have a dielectric. Okay, so over here, let's say the electric field is E0 for this system. Right? When you put a dielectric in between, what happens to the electric field? Can you guess? Exactly. So it becomes E becomes E0 over K. Okay, so the dielectric, and let me briefly tell you why this happens. So you have plus Q and minus Q here that creates this electric field, right? But what will happen is that this plus Q and minus Q will generate an induced electric field. So this plus Q will attract more of the pluses towards here and more of the minuses towards there. Okay, it will create a polarization inside it. So that polarization will create an induced electric field. Normally the electric field is in this direction, but there will be an induced electric field in the opposite direction. It will not be exactly matching the one that was applied, but it will reduce the effect by K. Okay, this is what's going on. So coming to the question is this. Why I made this question so complicated? Let me make it easier. So let's say this is R, this is 2R, and this is 3R. Okay? And I have a dielectric here. Okay? And there's a separation over there. So I have plus Q inside, minus Q outside, and it's a sphere. It's a sphere. So inside there's a sphere of plus Q, then in between, not filling it all the way, there's a dielectric, then outside there's minus Q. What is the capacitance of this system? How would you approach this problem?
I would find first electrical field with Gauss law, then potential, then capacitance.
Very good. So what is the electric field in here? E times area, that's the thing. E times area is Q over epsilon 0 times K. That's the thing. Do you see? So now it will be E equals to Q over 4 pi epsilon 0 K times R squared. That's the electric field for the inside. For the outside, it's the same as usual. Q over 4 pi epsilon 0 R squared. So you would start from outside and you would go in. Okay? So the way that I did it over here is I named this one A. For the record, this is when I teach in a bad way. So that you know that I also sometimes teach badly. I am aware of this situation right now. I just lost the performance, sorry. So, but live with it, please, for a while. So I have in my notes that VC minus VA is equal to integral negative R to 2R Q over 4 pi epsilon 0 K R squared dr. Do you agree with this? Yes? So what is then, so let me just skip a lot of stuff here. VA minus VC turns out to be Q over 8 pi epsilon 0 KR. Okay? If you do the mathematics, this is what comes out. And similarly, if you do it for the other part, VC minus VB, you get Q over 4 pi epsilon 0 times 1 over 2R minus 1 over 3R. So if you sum them up, VA minus VB, please try following it, and if you have any questions, just ask them. Do you have any questions? No? Did you follow all this?
We don't know what VA is like. We don't know their value. We just know the difference.
We just know the differences, and we only care about the differences. So VA minus VB turns out to be Q times K plus 3 over 24 pi epsilon 0 KR. What is the capacitance? It's Q over VAB, and it turns out to be 24 pi epsilon 0 KR over K plus 3. This is a typical question involving dielectrics. Was it hard?
Can it be an exam?
Yes, it can be in the exam. For example, we ask the same thing, exactly the same thing for a cylinder. That's a fair exam question. Can you do it? Why it's a good exam question? Because it has Gauss's law, it has symmetries, it has dielectrics, it has electric potential, it has capacitors. Just one question involving 4 chapters. That's why it's a good exam question.
John, why we don't find anything for R smaller than big R, like inside the...
Because yes, very good question. We are only interested in the potential difference between these two edges, A and B.
We don't need the...
We don't need outside, we don't need inside, we just need the potential difference in between.
It is conducting sphere, so there is no...
The inner and outer shells are conducting.
The inside, so
I think I should draw this part with this as well, right? So
So inner sphere is not conducting then.
what do you mean by inner sphere?
This one.
So inner blue one,
Yes.
inner blue, do you see inner blue?
Yes.
It's conducting. Outer blue, also conducting. In between, there is a spherical
So R
thing.
small r smaller than big R in that part there is no electric field.
There is no electric field there. Yes.
Potential da.
Potential is constant, right?
Why can't this be zero?
Then you set that potential to 0. You can't do that. Do you
Because
see?
it says Q, okay.
Do you have any other questions? Yes.
There were examples where we removed the dielectric with the
Yes. I will solve such examples next time as a part of example solution.
but it's those kind of questions.
Those kinds of questions are also good exam questions. But we already did the energy difference when you change the geometry of the system. So taking dielectric out, putting it in, is also that kind of a question. Should we do one really quickly? Let's do one really quickly. Servisler var, okay. Take good care.